Welcome to a lesson with Dr. Powell. In this video, we're going to look at a practice problem for derivative rules and taking derivatives. So let's take a look at this one right here. Now, something kind of important with derivative rules, and a lot of people just mess this up completely and they slaughter this because they think about derivatives as just being like, oh, let's just play around with symbols, and they don't really care what's going on. So like maybe it's like sine of cosine of x, and then maybe there's like times tangent x, and then all over maybe like x squared plus 1. Okay, now if they take a look at this, a lot of people will be tempted to saying, oh, I know the derivative of sine, it's cosine. So they just like replace symbols and they keep it the same form. But the problem with, there's a lot of problems with that. For one thing, derivatives change symbols, like different, like divisions, it does something with that. Multiplications, it does something with that. It changes form, or putting a function inside of another, it changes its form. There's a lot of things that change. You can't just simply replace symbols, and that's completely wrong. Please do not do something like this. We do not just replace everything with their derivatives as we're going through. Yeah, you might have an idea of like what's happening with the symbols in like certain small derivative rules, but really derivative rules are more than that. They're what's happening with all the operations. Multiplication, that's like a boxing thing. This quotient, that's similar. And also with like plugging one function into another, really up close, that looks like some kind of a multiplication of things. And by the way, in the derivative of whatever sine is, what you don't change the input from the function to its derivative. Like sine x, cosine, you're not going to be plugging in a different point at the computer derivative. You're computing at the same point that you originally had. So you don't change your inputs. So what does change is what's multiplied on. There's a lot of different things that happen here, and you can't just simply replace things. That shows that there's a lack of understanding on really what's going on here with derivatives. But that's a very common error. People think they know how to take derivatives if they do that, and they absolutely do not. So please keep that in mind as we go along. Pay attention to all these rules: quotient, product, chain rule, and all of that. I mean, a common thing here as well, if you see this 4 multiplied on, you may think in your mind, hey, that's like, I know derivative of 4, it's 0. Hey, that means the whole thing is 0 right here. Wow, so that part's gone. And no, please do not ever do something like that. This 4 multiplied on stays multiplied on. If you really like to do a product rule, you could. You could say 4 times this, right? So the derivative of 4 is 0. That part is gone. But there's another part where you leave the 4 alone and take the derivative of that part. Oh, that's what we usually do with constants. You leave it alone, multiply it on, right? It's the second part of the product rule. Okay, so right here, what we have is we have 4 times the derivative of this part. What's the derivative? So we think this is a chain rule. Tangent inverse of something. What's the derivative of tangent inverse? It's 1 over 1 plus the inside of tangent inverse squared, whatever's there. Notice notice that we're plugging in the same thing into the derivative of inverse tangent as what's going into inverse tangent, but there's a rate of change different thing that has to come into play with the chain rule, like how fast the input is changing is now different than just, like if it were x. So you have to speed it up by multiplying it by something here, or slowing it down depending on what it is. So we have, now we have to multiply this part by the derivative of this inside piece. E to the x squared, e to the quantity, e to the x squared plus 5. So keep in mind that's the whole thing. That's in an exponent completely over 2x. I'm going to use quotient rule. So we take the derivative of the top, which is, it's another chain rule, e to the x squared plus 5, right? E to the something. Derivative of e to the something is e to the something. Great, except you have to multiply it by the derivative of the inner side part. What's the derivative of x squared plus 5? That's just 2x. Okay, so the derivative of the top is this, but then you have to multiply the derivative of the top to the bottom. So that times the bottom, 2x. Then you subtract off, and that's a coincidence there. That's a 2x from there and there. I mean, I could have changed that, but anyways, keep that. This 2x comes from a different place than this 2x. This 2x comes from the denominator. This one comes from the derivative of x squared plus 5. Okay, but coincidences happen often. Please don't let them confuse you, and please don't think of it as a pattern. And keep in mind where it comes from, because finding false patterns is another very common mistake that people make with derivatives and things like that. Please do not, people like patterns, and that's good, but there's a lot of false patterns out there, so please be careful. Okay, so we have that's the top time, so the derivative of the top times the bottom, but then we subtract off, this would be, we take the top, e the quantity x squared plus 5, times the derivative of the bottom. The derivative of the bottom is just 2, okay? And all of that is over the bottom squared, the denominator squared, 2x quantity squared, which is just 4x squared. Woof! So that's the derivative. So this part right here that we multiplied on is the derivative of the inner part to the inverse tangent. All we've done so far is take the derivative of this part, this first part, 4 times the inverse tangent of that. Now we get to add to it, because derivatives do behave nicely across addition. That is a derivative property right there, where it actually just splits. It does exactly what you would imagine it doing. Derivative, even in the simple case when you don't really understand what's going on, derivative of the first part plus the derivative of the second part. Okay, so right here, derivative of this. Oh, how do you take the derivative of natural log of 5, 2x? Now, if you don't really know how to do that, you can think, actually, this is a nice change of base. Natural log of 5 is the same thing as, or the log base 5 is the same thing as natural log of the top divided by natural log of 5. This is a nice form to think of it in. You can always translate something like this to this form, and that's kind of nice, because this natural log of 5, that's a constant. I mean, you can think of this as just 1 over natural log of 5 as a constant times the function natural log of 2x. And so this is just a constant times natural log of 2x. Now, you could just take the derivative of natural log of 2x in this way, like with the chain, 1 over 2x, times the derivative of 2x, which is just 2. And you notice those 2's cancel. You just get 1 over x. We could have done that. And then, of course, 1 over natural log of 5 stays there. And so you would get 1 over natural log of 5 times 1 over x. Sure, that's great. But you could also remember that the derivative of natural log of 2x, think about natural log of 2x. Natural log of 2x is equal to the natural log of 2 plus the natural log of x. What's the derivative of natural log of 2? That's a constant. We put a constant number into a function, and we get a constant output, right? We get just a number output if we put a number in, and it's a fixed number, right? Derivative of this part is just 0. So really, in terms of if we're taking this is not equal that way. When we take a derivative, though, so of this, of natural log of 2x, we can think of natural log of 2x as being natural log of 2 plus natural log of x. This part will go to 0, and this part will go to 1 over x. So notice the derivative of natural log of 2x was simply just 1 over x multiplied by the constant natural log, 1 over natural log of 5. Okay, now this, without simplification, but I'm not focusing on simplification here, just on using derivative rules properly, would be correct. Okay, so this would be equal to y, that would be equal to y prime. And that is, sorry, got that funny line. And that's it. Thanks for watching.